Hello everyone, this is our lecture on lead-lag compensators. As you expect, lead-lag compensator is a compensator that combines the benefits of both lead and lag. Lead for changing the transient response behavior, and lag for steady state. So if we want to have everything together, a single lead or a single lag is not going to work. We have to combine. And instead of having one lead and one lag in cascade, we put both of them in a single compensator called lead lag, which has the following transfer function. So it has two poles and two zeros and a gain. Clearly you can see that this compensator has 5 parameters to choose: beta, gamma, Kc, T1 and T2. Now here, instead of that parameter alpha that we use for lead, here we used a similar thing, but we call it gamma. And here, to make both gamma and beta both bigger than 1, instead of, we had alpha in the numerator, in the denominator of the pole, so it was 1 over like T1 times alpha. Now we bring gamma, which is like 1 over alpha in here, which is bigger than 1. We bring gamma into the numerator of that pole and make it gamma over T1. So that's the same thing, doesn't really matter. We can say gamma here is the same as 1 over alpha of a lead. And then the two Kc's of each one, we multiply them together, and this Kc is basically the product of the gain of lead and lag together. So again, we have 5 parameters to choose from. The only limitation is both beta and gamma ought to be bigger than 1. And this is going to change the behavior of the system near 0 and everywhere else. Okay. Now, we can choose gamma and beta to be equal or not equal. Here we choose the case that they are not equal. So like general case, if they are equal means we are bringing down to 4 parameters instead of 5. So the first thing we do, from the transient response characteristic, we will determine the desired location of dominant poles. Then first, we draw the root locus of the uncompensated system. We draw the new poles on the same root locus, and then we determine the angle deficiency of the system the exact same way that we did for the lead compensator design. And then we say the lead portion of the lead lag, which is basically this first term here, this term, this guy here, that is responsible to provide that angle deficiency, phi. Then, in order to do that, since we have 2 parameters to choose, gamma and T1, to make that phi feasible, what we do is, again, you can see I only need to satisfy one condition, which is the angle contribution of the lead portion is phi, but I have 2 parameters, so I have basically infinitely many solutions to have. So what we typically do, we choose one of them and determine the other one. Okay, but you have so many solutions to choose from. Then what we want is the magnitude of the lead portion times the original transfer function to be equal to 1, okay, at the desired location, of course, and using that we will find the gain Kc. And then for the beta and T2, we do a similar approach. that we need to change, let's say, the constant kV of the system. So we choose beta to improve the kV number, and then knowing that the new kV is going to be Kc, the constant that we found in step number 4, times beta divided by gamma of original kV. And gamma is determined in step number 3, Kc is determined in step number 4. And since I have the original kV and the new kV, I can determine from this step number 5 beta. And then we choose T2 such that the magnitude of the lead lag term, is also equal to 1 at the desired location of the poles. And the angle contribution of that is not more than 5 degrees. Because if this magnitude is not equal to 1, then it's going to interfere with this portion. Because actually the magnitude of the whole thing at the desired location should be 1. So this term here, this lead term by Kc times this term should be equal to 1. So if one of them is quite off from 1, then the other will not be 1, okay? So the fact that we choose this to be 1 here means the other one should also be almost 1. And the thing that the angle contribution of the whole thing should be phi. So when we choose only the lead to provide such angle, then if we come here and make this contribution a big number, then that would reduce this angle phi, right? So here, the angle here is phi. Here, this angle contribution is a small negative number, so like -1, -2. So the whole angle contribution will be like phi minus 1 or phi minus 2, which is very similar to phi. But if this is like -20 degrees and phi is 40, then we are reducing basically half of phi through the lag portion. So the only effect of lag is not really changing the zero and pole portion of it. They are not there to contribute any angle. They are not there to change the gain. The only thing they do is to bump up this kV through the contribution of beta, and the lead portion will take care of the angle distribution, and then through phi and beta through steps basically 3 and 5 is what lead lag compensator all work together. Now to clarify this, let's look at this example together. So here again we have a system down below, unity feedback, G is 4 times S plus 0.5, and the dominant poles for this system are at -0.25 plus 1.98 for I, which gives us omega n of 2, zeta of 0.125, and kV of 8. Now we want to bump up zeta to 0.5 to make the overshoot go down. We want to bump up omega n at the same time also to make the settling time go down. And we want to bump up kV so that the steady state error goes down. So you see, in order to make the system response better, we are increasing zeta, omega n, and kV all. That makes settling time, steady state error, and overshoot to all go down. Now, how can we achieve everything together? Both transient and steady state response? The answer is a lead lag compensator that we are going to design, and then we want to plot the step and ramp response of both systems and watch the improvements. So what we do here is this. We go according to the steps. First thing is we determine the desired location of the dominant poles. By the way, again, these are dominant. It doesn't mean there are only 2 poles to the compensated system. No, because just the lead lag by itself has 2 poles. And the original system also here has 2 poles, so the compensated system is going to have 4 poles but we assume two of them are dominant. Okay, and we'll check whether that's the good assumption or not. So the first thing we want to do, find the location of the dominant using these two important things, that zeta and omega n are 0.5 and 5. Okay, so let's do this together. So what we do is, first, if you want, we can look at the root locus of the original system, which has numerator 4 and denominator is 1.5 and 0. So this is the original system that you can see, right? And if you want, you can see that if I find the closed loop transfer function for this system, the original one, C over R, which is going to be G over 1 plus G times 1, because H is 1, that is going to be 4 divided by S squared plus 0.5S plus 4, which means omega n squared is 4, and 2 zeta omega n is 0.5. And so from here you can clearly see that omega n is 2 and zeta is 0.125 or 1 over 8. Okay, now what we want is to change zeta and omega n. So the new zeta and new omega n, we want new zeta to be 0.5 and we need new omega n to be 5. So if we basically from here we form the characteristic polynomial, the dominant characteristic polynomial is it's gonna look like what? Or we can find even the location of dominant poles. If you remember, the dominant poles, if I call them S1 and 2, they were what? They were negative sigma plus minus omega d, or they were negative omega n times zeta plus and minus omega n times square root 1 minus zeta squared times I. So in this case, if I multiply, it's going to be negative 2.5 plus and minus 5 times square root of that, which is going to be, let me calculate it, 4.33. So these are the new location of the poles instead of these original ones that we had, right? So the original ones were quite closer. Now these are further away, and a simple gain adjustment is not going to achieve it. So what we are going to do, we need a lead for this portion, and then we need a lag compensator for the steady state. So this is our dominant pole. These are the dominant poles, these two guys. This is where we want the dominance to be. Now, we find the angle phi, the contribution of angle of the lead portion. And if you remember, the way to do it was we draw the root locus of the system. So if I draw the original root locus, which you just saw in MATLAB, but I want to do it here. So this is the original root locus. So you have the pole at 0, you have it 1 at negative 0.5, right? Like this. And then the angle 90 degrees. So you have something like this. And let me make it a little thicker. So it looks like this. And then one pole is here, one pole is there. This is at 0, this is at negative 0.5. Then here one goes up like that. And then the other one goes down like this. All right. So this is the original root locus. And now we want our dominant pole to be at this new location, negative 0.25 and 4.33. So it should come somewhere like here, where this one is negative 2.5 and this one is 4.33. And then we will find the angles from the original poles to the new pole. So if I connect here this vector and then this vector, and I call these angles again like phi 1 and this angle like phi 2, then I can say that the angle phi is 180 minus the summation of angles from original poles to the new pole plus the angles from original zeros to the new pole, but there is no zero to the original system, so it's just going to be simply this. And again, we need to find phi 1 and phi 2 through tricks. So phi 1 is not hard because I can find this angle, right? How much is this angle? Well, if you look, my original zeta is 0.5. And 0.5 means arc cosine of 0.5 is 60 degrees. So this angle here is 60 degrees. So clearly from here, phi 1 is 120. That's not too bad. And then what if you want phi 2? So for phi 2, I'm going to find this other angle, phi 3. And then I subtract 180 from that. And clearly you can see that phi 3 is tangent inverse of, if you look at this triangle here, it's the vertical portion, which is 4.33, divided by the horizontal one, which is the difference between 2.5 and 0.5, which is 2. So you find that, and then phi 2 is going to be 180 minus phi 3. And so when you combine everything together, you can see that phi is going to be the angle contribution. Let me find that out for you. So 55 degrees. So the lead portion should contribute 55 degrees to the whole system to move and reshape the root locus and make it pass through these new points. Good. Now, how can we achieve this? The angle of this lead portion at the desired location should be phi, which gives us basically one equation between gamma and theta, and then that should give us infinitely many solutions, right? And infinitely many solutions, of course, means we choose one of them in this case, and then we will find the other accordingly. So let me fix this. By the way, it's gamma, not gamma 1. So what we do is we use this step number 3. And step number 3 says the phase of S plus 1 over T1 divided by S plus gamma over T1 at S new location. This should be 55 degrees. And so here you clearly see I plug in that S into that, and knowing that 1 over T1 and gamma over T1 are just scalars, so it is going to be angle of negative 2.5 plus 1 over T1, which is the real part, plus 4.33i divided by negative 2.5 plus gamma over T1 plus 4.33 I, which is equal to, you know, when you have a complex number in numerator, complex number in denominator, you have to, the angle of the whole thing will be the angle of the numerator minus the angle of denominator. What is the angle of the numerator? Is tangent inverse of, it is tangent inverse of the imaginary part over the real part minus now the angle of the denominator, which you can find similarly this should be 55 degrees. Okay, and now you have the option to choose one of them. So to make life simpler, I can choose T1 from here to give me an angle, take it to the other side. So it's going to be tangent of something is equal to some angle. Then I take tangent from both sides to get this ratio equal to a number. And then since I know T1, then I can find gamma. So in this case, we would choose something and let's see. So if I want to go exactly according to your textbook, what your textbook did is quite interesting. So your textbook chose, because you know this 1 over T1 is what? That's the zero of the lead. Now it chose 1 over T1 to be exactly 0.5. So that term in numerator of the lead is S plus 0.5. Now, what's good about that? Well, if you look at your system has a what in it? S plus 0.5. So basically that S plus 0.5 in numerator of that will, when it's multiplied GC by G, that term and this term would cancel out. So it is trying to get rid of one of the zeros and poles and bring the order of system down, which has its advantages and disadvantages. The advantages, of course, bringing the system down makes calculations, approximations, and everything much better, much more accurate and easier. The bad thing is if this parameter you can tune it such that it is at 0.5 and cancels that pole, but if there is any small disturbance in the system, or especially in the value of the parameter that you are trying to tune for T1, if that number is such that it's not exactly, the zero is not exactly at 0.5, then those will not really cancel each other. But if we go with the suggestion of textbook to try to get rid of this 0.5, we cannot eliminate 0, right? Because 1 over T1 has to be a non-zero value. Cannot choose T1 to be infinity. So what we do, we make sure that 1 over T1 is equal to 0.5 to get rid of the pole, as I said. And so from here, basically T1 used to be 2. So that's your T1. Now, if I plug that over here and here, clearly this one, as I said, will give me an angle, which I take to the right-hand side. So this negative arctangent is equal to some angle. I multiply both sides by negative and then take tangent from both sides. The tangent of arctangent on the left would cancel. So I'm going to be left only with this. The right-hand side is an angle. Tangent of that is going to be a number. So what I'm going to be left with is this ratio is equal to a number. And in this ratio, the only unknown is gamma because T1 is known. So if I solve and from here, then I can find gamma. And you'll see that the gamma will be almost 10. So it is going to be 5.02 divided by 5, which is 10.04. Okay, so now I could find my T1 and gamma, and therefore this portion here, this lead portion, will be like S plus 0.5 divided by S plus 5.02. Okay, this is going to be the lead portion of my compensator, which contribute 55 degrees and reshape the transient response. Now I go back and say, fine, now I want gain Kc such that the magnitude of the original times the lead portion is only 1, right? So I go back here and say the magnitude of Kc times the lead portion, which is S plus 0.5 divided by S plus 5.02 times the original G, which was 4 divided by S times S plus 0.5. This thing at the new pole location, which is negative 2.5 plus 433i, this should be equal to 1. Now this is the good part, that because I chose that pole to be the same as this 0 and that pole, now these two would cancel out, which makes our calculation significantly easier. So if I plug everything in, everything is known except for Kc, and from here I can find my Kc to be, let me look at that. So it is going to be 6.26 to make such thing happen. Okay, so the third parameter is now known, Kc, and the lead portion is completely known. Now we go to the lag portion, where the goal is to drive Kv to a number 10 times bigger. So we want to go from 8 to 80. And so what we do is we use this formula here, that the new Kv is beta Kc over gamma times old Kv. Okay, so if I come here, say that the new Kv, if I call it Kv hat, is as you can see, the old Kv times Kc times beta divided by gamma, right? Which is this formula here. Now, I assume we have every number that we wanted except for beta, right? Because gamma I found in the previous section. Gamma is known, 10.04, and Kc, we just found it. The new Kv is 80, the old Kv is 8, right? This is 6.26. This guy is 10.04. From here, everything is known except for beta, from which if you solve for beta, you're going to get 1604. So you need such gain to make sure that the Kv is bumped up by a factor of 10. Now that I know my Kc and beta, the last parameter is T2. I just need to make sure that now the magnitude contribution of the lag portion is almost like nothing, just 1, and the angle contribution of that is almost also a very small number. And to make that happen, we typically need to make sure that both poles and zeros are close to origin. And here the ratio between them, the ratio between these locations, one of them being 1 over T2, the other one 1 over beta T2. So you see that the pole is quite closer to the origin than the 0. How many times closer? 16 times, right? So we choose T2 to be such that 1 over T2, which is the 0, which is further away for the lag, is still less than 1, still small, so that the pole is much closer. So we need a T2 bigger than 1 for sure, and such that, again, the angle contribution should be less than 0.5 and the magnitude contribution is 1. And you might say, well, how do I check that? Well, you just choose a number for T2 and check like this. So you say, well, let's say T2 is equal to, your textbook says 5. Now let me choose a smaller number like 3 and show you that maybe that is not working. So I choose 3. So the lag portion will be what? It's going to be S plus 1 over T2, which is 1 over 3, divided by S plus 1 over 3 times beta. Now, what is the magnitude of this guy at the new pole? This should be close to 1, and also the angle that this guy contributes at the new pole this should also be between 0 degrees and 5 degrees, right? Negative 5 degrees. So again, at this new location. Now, is that the case? Let's check it with MATLAB. So I define two complex numbers, one for numerator, one for denominator, and use the absolute value command in MATLAB to get them and divide. So I say S is equal to negative 2.5 plus 433i. Now Z1 is equal to S plus 1 over 3, and Z2 is equal to S plus 1 over 3 times 1604. And now I say, what is the absolute value of Z1, magnitude of Z1 divided by magnitude of Z2? And you see that, well, that's quite nice. 97, that's close to 1. Now how about the phase of? We use the command arg, right? Phase of numerator minus phase of denominator, which is the phase of a ratio, right? And it does not like the command arg. Okay, so wasn't it the arg? Should be, but now arg, I guess, is what we use in our lectures, really. So if I just look at the complex numbers, so I have conjugate, image, real, ij, and it was ang, I guess, A-N-G. ABS is the magnitude, and angle, yeah, the command is called angle, and what it returns is in radians. So we have to use command angle, not arg. Arg is what we use in our lecture, so we have to be careful. So we get the angle of this minus the angle of that, and then multiply the whole thing to convert it into degrees. We multiply it by 180 and divide it by pi. So you see it's -3 degrees, so that's not too bad, right? So it seems like 3 is also working. Now your textbook says 5 instead of 3, so this one be 5, and this one be also 5 again. And then if I look at the magnitudes, this is close to 1. If I look at the angle, it is smaller, right? So you see when I make t bigger, what happens? The absolute value of this part is getting closer to 1. So instead of 0.97, now it's 0.98. And the angle contribution is closer to 0. It was -3 degrees, now it's -1.9. Okay, so even 3 might work too, but maybe if I make T1 to be, let me just change it to something else. Maybe somebody is enticed to say, how about 1.5? Okay, so now if we do it with 1.5, and we look at the magnitude, 0.94 is getting away from 1, and the angle is clearly more than 5 degrees. So you can, by checking through MATLAB, you can find which range, but your textbook, again, it's just a suggestion. So your textbook says T2 equal 5 is good. To me, T2 equal 3 is also not bad. So that is fine. And so once you put everything together, now your compensator GC will be KC gain 6.26 times the lead portion, which is, it was S plus 0.5, correct? If I'm not mistaken. No, that is the lag portion. The lag portion is, let's make sure. And we can go back and check. So the 16, yes. This is the lead portion. 0.05, 5.02. And then the lag portion is this. Okay, so 5 and 5.02. So this portion is the lead portion, and this is the lag portion, which is S plus 1 over T2. If you choose T2 to be 5, so this is going to be 0.2, and this is going to be 0.2 divided by 16, which is going to be 0.0125. Okay. So that is going to be the compensator. And now I need to multiply that by G. So that whole thing is multiplied by G, which was 4 times S plus 0.5. And when you multiply, then that one and this one would cancel out. So that was the root locus of the original system that you saw. Now in a separate figure for you, I am going to root locus the new system, where the assuming that the S.5 is canceling, so I'm not gonna show it. So the only remaining term is 6.26 times S plus 0.2, 6.06, and there was a gain of 4. So 4 times 6 times 1 and 0.2, that's the numerator, and then the denominator is these two terms multiplied, and then S and S plus 1, I assume, right? Let me double check. S and S plus 0.5, where the 0.5 would go away, so there is only S and then these two terms, S, and that is going to make it S and 5.02 and 1. When you multiply S by the first term, right, that's going to be this, and then you convert with this one, 0.125. 0.125. Okay, so if you do that, now this is the new root locus. You can put it side by side with the original system. And first of all, clearly you see that it is shifted to the left, because here the asymptotes were at, or not just asymptote, the root locus was at 0.285. Now this is at what? At almost negative 2.5. So it's shifted 10 times to the left, which makes the real part of the poles 10 times to the left, which makes zeta what it needs to be an omega n. So, and also the behavior of the system near 0 is changed to make the steady state error what it has to be. Okay, so this is how you design a root locus. It's a root locus designed for a lead lag compensator.